In this video, we'll answer the question, why do we learn Fourier series? And more specifically, why do we learn Fourier cosine series and Fourier sine series? So I went over the problem here in more details, but we'll get to the answer pretty soon. So, first of all, if we have an example like this one, a partial differential equation problem with boundary conditions, with initial conditions, but please pay attention to this one. This one is the one that it's important. We have that the solution at time 0 equals a function f of x, and this function f of x is given here as x times pi minus x. And we've done problems like this before, so that's why I'm not going to go through the details of how we solve it, because I have here all the steps. I'm just going to leave the screen so that you can pause and look over each detail. And I also, if you notice, I skipped really quickly. If lambda equals 0, I just said is a trivial case, which means x of x is going to be 0. And if lambda equals 0, then again we have the trivial case, but I actually discuss in detail the case of lambda greater than 0. Anyway, the case lambda greater than 0 gives us two complex solutions, which we write like this, which helps us figure out that x of x is c1 cosine of square root of lambda x plus c2 sine of square root of lambda x. And from this equation here, c2 equals 0 will give us the trivial case, but sine of square root of lambda pi equals 0 means lambda equal n squared, and for n equals 1, 2, 3, and so on, these are the eigenvalues. Now, what does that mean? It means x of x is equal to c2 sine of nx, but it's a sum or a linear combination of solutions of this form. So x of if x sub n of x, it's actually sum as n equals 1 to infinity of c sub n sine of nx, which are the eigenfunctions. And here is the moment where we should kind of figure out why we learn Fourier sine series specifically. Well, just look at these eigenfunctions. What are they? They are functions of sine of x. So we want to find the coefficients in front of sine of x, right? I actually did part 2 where I figure out what t of t is, but let's get back to this x sub n, which is c sub n sine of nx. So this piece here, right, this one, it's actually at time 0, it's actually equal to f of x based on this initial condition that we started with, this one here that I told you it's very important. So when you set t equals 0 and then u of x or x of x is going to be equal to f of x. So going back here, this is the moment where how can we find c sub n? Well, c sub n are coefficients of the Fourier sine series. So what we do here, we calculate c sub n as 2 over pi integral from 0 to pi f of x sine of nx dx. So basically using the formula for finding coefficients of a Fourier sine series. And again, why Fourier sine series? Because it's sine of nx. If it was cosine, then I would use the formula for cosine, Fourier cosine series. So here, the actual work, I skipped many steps because if you notice, looking at this, you actually have 2 integration by parts, actually 3 integration by parts. But I wanted to get to this point where we actually calculate c sub n because that's the question that we asked. So basically, u of x and t, it's sum as n equal 1 to infinity of all this c sub n sine of nx e to negative 5n squared t. So why do we we learn Fourier sine series so that we can find the coefficients of a solution of a heat problem, for example, or even a wave one. So here it is. I just open it so that it's pretty, you can see the whole thing. Well, I do hope you were questioning why we learn it, and I hope I answered the question why we learn it.